Hello, everybody. I want to continue talking about trees. I could go on to talk about the red-black tree, which I might do later, but I'd like to get out of binary search trees for a while and talk about B trees. B trees and their relative B plus trees are really the workhorses of databases. They're very useful for large amounts of data. And they're similar to a binary search tree, except that they have more pointers at each level. They're not down to 2 pointers at each level. You can have many more. The terminology for B trees is all over the place. You can find different definitions, and nobody seems to have any idea what the B stands for. One suggestion is it stands for balanced, although I will admit one of the people who invented it, his last name is B. It begins with B, so maybe that's what it's for. So what is it? All the nodes we will look at as having the same size. We're going to talk about a B tree of order M. So if it has order M, then it could have M key values and M plus 1 pointers. Now, some of these keys might be empty, and some pointers might be null. All leaf nodes are at the same level. So when we insert or delete, we have to maintain that, and that's difficult. All nodes except the root and the leaf node have at least the ceiling of M over 2 minus 1 children. Now, what's this business with ceiling? Well, suppose we have M equals 3. 3 over 2, if we don't use integer division, is 1.5. We raise that to the next integer above it. We get 2. So we have 2 minus 1, and the minimum we can have is 1 child. Now, if M were 4, we'd have 4 over 2, which is 2, and the ceiling of the integer is itself, so it'll still be 2, and we'd be 2 minus 1 again. Now, the root has to have at least 2 children if it's not a leaf. Those are the rules. Here's an example. I'm going to talk about a M is 3. So remember I said if M is 3, we have M key values and M plus 1 pointers. So each node will have 3 keys in it and 4 pointers. Some of the keys won't be there yet, and the pointers won't mean anything until they get in there. The idea is that this node splits the whole universe of key values into 4 different pieces. If you have a key value that is less than key 1, then you go to pointer 0 to find it. If it's equal to key 1, you're done. If it's greater than key 1 but less than key 2, you go to pointer 1 here to find it. If it's greater than key 2 but less than key 3, you go to this pointer. And if it's greater than key 3, you go to the final pointer. Now, of course, that means that the keys are in order. They have to be in increasing order. And in this particular setup, we have the rule that keys are unique. That's often true in databases, that keys must be unique. Now, I've built an example tree. This is a little smaller. It's M equals 2. It's sometimes called a 2-3 tree. In my tree here, I have pardon me, I have 3 pointers, so it's still m equals 3. I have 3 keys and 4 pointers. And in the root, which is the top node there, this one right here, I have 50, 90, and 200. Everything with key less than 50 is in this node, 20, 35, and 47. Everything with key greater than 50 but less than 90 is in this node. Everything with key greater than 90 and less than 200 is in this node. And then finally, everything above 200 is in the last node. Now, that's where we're going to begin. I want to see what happens as we add things. So let's try to add 160. One way to do it, not the only way, is to go bottom up. Some people prefer to go top down. They say it means less transversal, but I think it's easier to go this way at the moment. You look in the root. 160 belongs between 90 and 200. So let's go down to between 90 and 200. Excuse me. All right, we go down to between 90 and 200. Well, we'd like to insert the 160 there. But there's a room. We're only allowed 3 of these. And we can't go to a lower level because all the leaves have to be at the same level. So the only choice is to split this node. Now what that means is we're going to create 2 nodes. We'd like to make them as equal as possible, but unfortunately we're going to have to make them a node with 2 elements in it and a node with 1 element in it. Notice I took the 94 and the 120 and I took the 170. What did I do? What am I going to do with the 160? I'm going to move it upstairs. I'm going to remember 160, everything greater than it, less than it is over here. Everything greater than it is over here. So I could put 160 there. That would make sense. However, the minute I try to put 160 in, I've got 4 things instead of 3. So again, I look back here. Pardon me. I have 50, 90, 160, and 200. The only way out is to split it the same way I did before. So I move the first 2 into their own node, and the last one into its own node, and 160 gets pointers to those, and these pointers stay put. They haven't changed, and these pointers haven't changed, so I don't have to do anything special. That's the way it's done. Now I could, if I were in a strange mood, I could try to have you write a program to do the insertion or deletion. I think it's just not something we want to do. I know it's not something you want to do, but it's not something I want to do either. I've looked at some programs to do it on the web, and I think one of them is like 30 pages long when I put it into here. And I don't really want to go through that. And it's not necessary because we're more interested in the idea of what this is used for and how it is set up. So instead, I'm going to have 2 simpler homeworks on this. The first homework will be homework 19. And what it says is, consider a 2-3 B tree. We have 3 pointers and 2 keys. I'm starting out with this tree. It has 4 elements in it, 525, 367, 525, 438, and 612. I want you to add 805. So first you've got to compare 805 to 525. Should it go this way or that way? Whichever way it goes, you have to compare it to the items in there. And then if you can put it in to the node without disturbing anything, you do. So for example, if it were to go here, that would not violate anything because you can have two nodes, two keys. Then I say, do that one, and now add 716 to the result. And then after you do those two, add 490 to the result. And then after you do those three, add 110 to the result. Now I don't want one answer at the end, that's part 4. I want you to show me it along the way. I want an answer to part 1, an answer to part 2, part 3, part 4. The answer would basically be to take this and make the changes in it and add any nodes you have to add. The way I created those nodes was to use an insert table. Seemed to be the easiest way to get it in. The second problem is actually a programming problem, but I don't think it's beyond you at all. I'm going to work with a 3-4 tree. And the first thing I did was decide how I wanted to define the tree and the nodes. I wanted the tree to be a class, and each element of it should be a node. So I defined a root that points to a B node, and that's the beginning of the tree. Up here, I defined the B node. We have a 3-4 tree. That means we have 3 keys possible in each of the nodes, and we have 4 pointers possible. I initialized all 4 of them to null to save me from having to do that every time I created one. Also, sometimes you need to know if you're at a leaf. So I put a Boolean variable leaf in it from what I was seeing on the web that you need something like that. And then I added the number of keys that we have in there already. I may have gotten it from the web, but I think it's important that you know how many keys you have filled in the node. Now that's the maximum, the size of the array is always 3, but sometimes we've only got 1 thing in it or 2 things in it, and n keys tells us how many we have in it. Then what I'd like to do is write a program to print it out in order. In order came from when we were doing binary trees. So let's extend in order to this particular example. I'll show you what I mean by in order. Say we're doing in order of this tree. I go to the root. It has a left child. I go to its left child. I go to this node. It has a pointer, the leftmost pointer. I go to that node. Now, in this node, null, so I write the parent, 50, 20. I check the next pointer. I write the parent. I check the next pointer. I write the parent. I check the next pointer. All of these are done. Now I can write the 50, which is the same as the value in the parent would be if we were doing binary. And then we go to the next pointer and do the same thing. Then when we pop up, we go to the we see if there's another key. If there is, write it and check its last pointer here to see if there's anything there. When you finish with these and that, you go up to the one above it, and then you start down the other side. So it's very similar to the binary tree. It's all the pointers. And the items in a pointer are written, the way it's written is the items in the pointer, the key, the items in the next pointer, the key, the items in the next pointer, so on and so on. It is recursive. And be careful. It's pretty easy to start off because you can count the number of keys and you can say, well, I have a pointer and then a key and a pointer and a key and then a pointer and a key. But you can't forget you have this one here. You'll have one extra pointer that you have to take care of when you're doing the recursion. So what I would have an in order, and then the in order is going to call a recursive function. It's going to call the function in order help root. And that's the recursion. You're going to write a program that starts at a B node and writes out everything below it. You'll notice that I fixed it so that you're never going to get a null down here. If you're seeing a null, well, I would suggest you might want to do that. Pardon me, I gave away something there. Now to test this, considering all the trouble you people have had with reading files, and I understand that, I thought we'd better not try that this time. I'll actually set it up, and you won't have to worry about reading any files. So I created a very simple test case. The root has two keys in it. 0 is 40 and 1 is 60. The number of keys is 2. The pointers, there have to be 3 if there are 2 keys. I gave each of them a new node. Then I made each of them a leaf, and I gave each of them 2 keys, and then I gave each of them keys values, and I didn't have to do anything with the pointers because I originally initialized them as null automatically, so I didn't have to do all that work. And then I tested it within order, and my results were that. So that's basically what you're playing around with. See what you can do. It looks like I put this on the same one as the other one, so I'll wipe this out when I send it to you. Now, are there any questions? Oh, well, I can't ask you that. So